let's summarize our construction part. In PMMC instrument, we have the fixed system, the moving system, spring, bearing and scale. Okay. The purpose of the field system is to provide the main magnetic field flux similar to the DC machine field flux. ठीक है यहाँ तक? But in case of DC machine, the rotation is complete, the circle in 360 degree. But in case of your PMMC instrument, the limitation is rotated, the limitation is fixed from here to here, that is provided by stopper. ठीक है यहाँ तक? Now, in case of PMMC instrument, the magnetic field produced by the permanent magnet is highest, whose range is from 0.1 to 1 Weber per meter square or 1 Tesla. This is the highest magnetic field among all the instrument. That's why we can use eddy current damping, because eddy current damping is used on those instruments where the magnetic field is highest. But if you see your comparison with moving PMMC instrument with MI, in case of moving iron instrument, the type of damping is air damping. Air damping, because in case of MI system, in case of moving iron system, the fixed system is air core. Is what? Air core. That's why the magnetic field is lower as compared to your PMMC instrument. That's why we, in case of MI instrument, they use the air damping, but in our PMMC instrument we use eddy current damping just because of high magnetic field provided by the fixed system. Now it is having highest magnetic field, so no need to shielding. But in general, the shielding material is nickel ferrous, NiFe, nickel ferromagnetic material use करते हैं हम shielding के लिए. और अगर इसमें मटेरियल की बात करें तो यू शेप के मटेरियल यूज करे जाते थे परमानेंट मैग्नेट. अब मॉडर्न डेज में जो है एल्निको यूज किया जाता है, एंड एल्निको इज अ कंपोजिशन ऑफ 3 थिंग, एल्यूमिनियम, निकल, एलॉय. यू कैन टेक परसेंटेज ऑफ दैट इज आल्सो इंपॉर्टेंट. आई होप इतनी बात समझ में आ गई होगी. नाउ इसके बाद हमने इलेक्ट्रोमैग्नेट और परमानेंट मैग्नेट में अंतर भी बता दिया था. परमानेंट मैग्नेट में मैग्नेटिक फील्ड फिक्स रहेगी, एज के साथ जैसे जैसे एज बढ़ती जाएगी इसकी जो मैग्नेटिक फील्ड है वो वीक होती जाएगी. इसका जो असर है उसके डिफ्लेक्टिंग टॉर्क और रीडिंग पे पड़ेगा. क्लियर है? और इसका क्या इफेक्ट होगा वो भी हम अपने न्यूमेरिकल में काउंट करेंगे. देन बट इलेक्ट्रोमैग्नेट में अगर आपने देखा था जो फ्लेक्स है वो कंट्रोलिंग है. और हाउ वी कैन मेड योर इलेक्ट्रोमैग्नेट, जस्ट टेक एन वन आयरन कोर एंड रैप द वाइंडिंग एंड गिव यू सप्लाई. आयरन कोर और इंक्रीज योर लेवल ऑफ मैग्नेटिक फ्लक्स. ठीक है यहाँ तक? फिर हमने क्या देखा था? मूविंग सिस्टम देखा था. मूविंग सिस्टम जो है सिलेंड्रिकल कोर, कॉइल और एल्युमिनियम का 3 चीजों का मिक्सचर है. जो सिलेंड्रिकल कोर है इस पर हम क्या करते हैं, एल्युमिनियम फ्रेम, जो सिलेंड्रिकल कोर है उसको एल्युमिनियम फ्रेम के अंदर रखते हैं और उस एल्युमिनियम फ्रेम के ऊपर हम क्या कर देते हैं, वाइंडिंग ब्रैक कर देते हैं. और जो सिलेंड्रिकल कोर है उसका एक और पर्पस भी अगर हम बात करें तो सिलेंड्रिकल कोर मेन पर्पस इज टू प्रोवाइड सील्डिंग फॉर द मूविंग कॉइल, टू प्रोवाइड सील्डिंग फॉर द मूविंग कॉइल. एंड एल्युमिनियम फ्रेम इज यूज्ड टू हैव मूविंग कॉइल. Okay, and aluminum is used in case of moving coil because moving system causes a friction error, and to have minimum torque weight, to have minimum friction error, torque weight ratio should be high. और torque weight ratio high होने के लिए देखिए क्या करेगा, टॉर्क वेट रेशियो, टॉर्क तो हाई रहेगा. वो कैसे रहेगा? क्योंकि टॉर्क इज प्रोपोर्शनल टू मैग्नेटिक फील्ड. मैग्नेटिक फील्ड तो हाई है, बट एल्युमिनियम यूज करने से, क्योंकि एल्युमिनियम जो है लाइट वेटेड होगा, एल्युमिनियम वेट कम होगा तो उसका टॉर्क वेट रेशियो क्या होगा? हाई. सो जो पीएमएमसी इंस्ट्रूमेंट है इसमें मिनिमम फ्रिक्शन एरर होगी क्योंकि इसका टॉर्क वेट रेशियो जो है वो हाई होता है. टॉर्क वेट रेशियो कैसे हाई होगा मैं बता ही दिया. टॉर्क जो है डायरेक्टली प्रोपोर्शनल मैग्नेटिक फील्ड के आएगा, और जो एल्युमिनियम है उसका वेट कम होता है. दैट्स व्हाई इट टॉर्क वेट रेशियो इज high. And coil is to just carry the current which we have to measure. So this is about the moving system. And the next one is what? Spring. In case of PMMC instrument, we will use constant and magnet or phosphor bronze type instrument, and that is called spiral spring. Its quantity is 2. In case of your PMMC instrument, it is carrying current, but in case of moving iron, they don't carry current. So in case of PMMC instrument, if the spring breaks out, then there is no deflecting torque, there is no reading. But in case of MI instrument, if spring break, then you can have something. Okay. एंड इट इज मटेरियल भी हमने डिस्कस कर ही लिया है। अगर हम बेयरिंग की बात करें तो टॉप और बॉटम एंड पे हमें दो बेयरिंग चाहिए, बिकॉज वी आर हैविंग मूविंग सिस्टम एंड टू मूविंग सिस्टम वी यूज बेयरिंग एंड द स्केल। इन केस ऑफ पीएमएमसी इंस्ट्रूमेंट वी यूज लीनियर स्केल, एंड लीनियर स्केल क्यों यूज करते हैं उसका भी हम रीजन दे ही देंगे, ठीक है यहाँ तक। और लास्ट वन पॉइंट जो था, एक मैग्नेटिक फील्ड जो हमारी परमानेंट मैग्नेटिक फील्ड से मिलेगी और एक मैग्नेटिक फील्ड जो है वो करंट कैरिंग कंडक्टर की वजह से मिलेगी। दो मैग्नेटिक फील्ड आएंगी, आपस में इंटरेक्ट करेंगी और उसकी वजह से क्या आएगा, टॉर्क आएगा। इस टॉर्क की इक्वेशन को हमें क्या करना है, ड्राइव करना है। सो दिस इज ऑल अबाउट योर कंस्ट्रक्शन डायग्राम। आई होप सो ये समझ में आ गया होगा। नाउ वी विल डिस्कस वर्किंग एंड द टॉर्क इक्वेशन ऑफ द पीएमएमसी इंस्ट्रूमेंट। सो स्टार्ट करते हैं टॉर्क एंड वर्किंग पार्ट ऑफ द पीएमएमसी इंस्ट्रूमेंट। Now let's take next part of the PMMC instrument, that is working and torque, deflecting torque equation. So working and deflecting torque equation. This is the second point about your PMMC instrument. So first we will see the working. So first point अगर देखें हम यहाँ पर, when a current carrying conductor is placed in a magnetic field, when a current carrying conductor is placed in a magnetic field, it experiences a mechanical force whose direction is given by Fleming left hand rule. तो सबसे पहले हम देख लेते हैं कि Fleming left hand rule होता क्या है, देखिए जरा समझिएगा। So कोई एक मैग्नेटिक फील्ड है, सपोज this magnetic field is into the page. This is magnetic field and it is into the page, into a page. So it is a magnetic field. Now when a current carrying conductor is placed in the magnetic field, suppose this is a conductor which is carrying current in this direction. This is your conductor and this is carrying current in this direction. Listen carefully. A conductor whose length is L is carrying current I and this is the magnetic field into the page. फिर से ध्यान, जब किसी मैग्नेटिक फील्ड में किसी कंडक्टर को, जब किसी करंट कैरिंग कंडक्टर को रखा जाता है, then that magnetic field experience will give a force on that conductor. That mechanical force direction is given by Fleming left hand rule. फिर से ध्यान से समझ लीजिएगा, जब किसी करंट कैरिंग कंडक्टर को किसी एक्सटर्नल मैग्नेटिक फील्ड में रखा जाता है तो उस पर क्या लगता है, एक मैकेनिकल फोर्स लगता है और उस मैकेनिकल फोर्स की जो डायरेक्शन है वो फ्लेमिंग लेफ्ट हैंड रूल से निकालते हैं। तो देखिए पहले तो हम फ्लेमिंग लेफ्ट रूल समझ लें और जो फोर्स है मैकेनिकल फोर्स, दैट इज आल्सो कॉल्ड लॉरेंज फोर्स, उसको समझ लें। सो देखिए फ्लेमिंग लेफ्ट हैंड रूल में क्या है, this index finger is in the direction of magnetic field and this mid finger is in the direction of current and this thumb will give you the direction of force. तो ये जो हमारी, these are the three mutually perpendicular things: magnetic field, current direction and the direction of force. Just apply Fleming left hand rule. Your magnetic field is inside and your current is like that, upside. Now it is upside, so your force is left hand side, okay, okay. So this force is given by F equals to BIL sin theta, ठीक है यहाँ तक। Now since this is the angle between your current carrying conductor and the magnetic field, so this sin theta equals to 1, then your force will be maximum. When sin theta is 1, that is phi equals to 90, then your force will be maximum. And sin theta is maximum when your magnetic field is radial magnetic field. Okay. So this is just introduction about your Lorentz force, Fleming left hand rule. Okay. Now let's start our working. Now, when a current carrying conductor, when a current carrying, when a current carrying conductor is placed, when a current carrying conductor is placed in a magnetic field, in a magnetic field, okay, that magnetic field is permanent magnetic field, permanent magnet field. In case of our PMMC instrument, when a current carrying conductor is placed in a magnetic field, in which magnetic field? The permanent magnetic field, and which is the current carrying conductor, and this is a moving coil current, moving coil current. ठीक है यहाँ तक बात? So when a current carrying conductor is placed in a magnetic field, it experience a mechanical force. It experiences a mechanical force, that is also called Lorentz force. Lorentz force. When a current carrying conductor is placed in a magnetic field, it experiences a mechanical force whose direction is given by Fleming left hand rule. ठीक है यहां तक? बट यही जो प्रिंसिपल होगा, इट इज डीसी प्रिंसिपल. व्हेन ए करंट कैरिंग कंडक्टर इज प्लेस्ड इन ए मैग्नेटिक फील्ड, it experiences a mechanical force whose direction is given by Fleming left hand rule. It is a working principle of all DC motor. It is similar to what? Similar to DC motor principle. Similar to DC motor principle. Motor principle with a limited rotation. With लिमिटेड रोटेशन. ठीक है यहाँ तक? क्यों लिमिटेड रोटेशन है भाई? क्योंकि जो डीसी मोटर है उसमें तो जो कॉइल है वो 360 डिग्री मूव करती है 2 पाई रेडियन में. ठीक है, बट यहाँ पर जो हमारा इंस्ट्रूमेंट में जो पॉइंटर है, दैट इज हैविंग पर्टिकुलर रोटेशन. ओके, दैट्स व्हाई आई यूज लिमिटेड रोटेशन, एंड लिमिटेड रोटेशन इज प्रोवाइडेड बाय स्टॉपर ऑन द लेफ्ट एंड राइट हैंड साइड. सो दिस इज योर working principle theory. Now let's see the diagram how we can get a force in case of a PMMC instrument. Let's again draw that diagram of cross-sectional view of that diagram. Okay, so let's draw. So we are having the permanent magnets. This is our permanent magnets. Just wait, my art is not perfect as it should be. Okay, now this is your permanent magnetic field. Okay, and the permanent magnetic field polarities are north to south. ठीक है यहाँ तक? Now in that we are having a coil, a rectangular coil. We are having a rectangular coil on aluminum frame. Okay, so this is your current in and this is current out, so this is current direction. Okay, I hope so ये बात समझ में आ रही होगी अब आप लोगों को. Now I can draw more clear picture of that also. If you take this diagram like that, if you take like that, then it is also correct. Okay, so it is current in, it is current out, it is current out ना. ठीक है यहाँ तक? This is A point and this is your B point. From one terminal current is entering, from another terminal current is out. Okay, now let's draw the direction of magnetic field also, so that we can apply your Fleming left hand rule and how it will have a rotation of that. Okay, so this is the direction of magnetic field. Okay, now Fleming left hand rule लगाने के लिए मुझे क्या चाहिए? First thing, I need the direction of magnetic field. Yes, we have north to south. Then I need the direction of current that we have in this conductor. As suppose it is A, It is B. Is it C and D? Let's correct its name also. Then in A to B it is downward, from C to D it is upward. Okay. Now let's find out the direction of force from the Fleming left hand rule. So Fleming left hand rule direction is this, and the current direction is this. Okay, just see this diagram. When you apply your Fleming left hand rule to find the direction of force, so this force is upward. This force is upward. Okay, so I just take this direction F. Okay, now if you apply this diagram, then if you apply this for this, it is like that. Okay, so it is just like that. So you are having such type of rotation like that of your moving coil. Okay, so when a current carrying conductor is placed in a magnetic field, like when a current carrying conductor is placed in a magnetic field, this is your moving coil is a current carrying conductor placed in a permanent magnetic field. That permanent magnetic field will exert a mechanical force on that coil whose direction is given by Fleming left hand rule, and that force is called Lorentz force. Now see, this is your force, this is your force. So this coil will rotate like that. Okay, so this is about your diagram of PMMC instrument. ठीक है यहाँ तक? Now this force is like that. F is equals to B I L sin theta. But sin theta is 90 degree, because your magnetic field is radial. Magnetic field is radial. That's why this angle is 90. Okay. So if you apply this, then F is equals to what? Just BIL. This is the equation number 1. Okay. Now let's second part of this thing also. Now if you draw the one part of this diagram, let's draw with this pen. Now I just take one more diagram of this. This is your cylindrical core. On that you are having a aluminum former, and here we are having this force F, and we are having this force F. So this is your pointer, and this is the radius of your cylindrical. Okay, this thing also. Now if you take total force is equals to what? Ft is equals to, or the resultant force is F minus F, that is 2F. So from the equation first, just put this value 2 into BIL, that is equation number 2. ठीक है यहाँ तक? So it is 2BIL. Now torque is what? Torque is Fr. Okay, so just it is 2BIL into R. Now just take 2R with common. It is BIL into 2R. Because dia is 2R, na? Dia is 2 times of radius, so it is D. Then, so your torque, the deflecting torque equation is this. I hope so. ये बात समझ में अब आ गई होगी आप लोगों को. So your deflecting torque is this. Now this is the equation corresponding to the 1 turn. If your moving coil is having n number of turns around that, then your torque equation becomes, the deflecting torque equation becomes NBILD, the equation number 2. This is your deflecting torque equation of the PMMC instrument. Clear है यहाँ तक बात? Hopefully ये बात समझ में आ गई होगी. Now I just erasing your diagram. अगर अब अगले पार्ट में देखें तो देखें हमने डिफ्लेक्टिंग टॉर्क इक्वेशन तो इस इंस्ट्रूमेंट की निकाल ली है, बट अब हम इससे चेक करना चाहते हैं कि हमारा जो डिफ्लेक्टिंग टॉर्क है वो किस किस चीज के प्रोपोर्शनल है. सो फर्स्ट अगर हम पॉइंट देखें, TD, द डिफ्लेक्टिंग टॉर्क इज डायरेक्टली प्रोपोर्शनल टू द करंट. द डिफ्लेक्टिंग टॉर्क इज डायरेक्टली प्रोपोर्शनल टू द क्वांटिटी अंडर measurement. Okay. So when your deflecting torque is directly proportional to the quantity under measurement, that instrument is it is an ammeter. It works as an ammeter. Okay, this is an ammeter. The next point we will see, your deflecting torque is proportional to your magnetic field of what? Permanent magnet. It is the directly proportional to the magnetic field, directly proportional to the magnetic field of permanent magnet. And keep in your mind, this current is the moving coil current. This current is what? Moving coil current. Agree? Now, next thing about your torque is what? Torque is directly proportional to number of turns. Torque is directly proportional to length of your core, and TD is directly proportional to dia. So these are some point about your deflecting torque. Okay. Now, under steady state condition, or under the balance condition, the deflecting torque is proportional to the controlling torque, and the controlling torque is provided by the spring, because in case of your PMC instrument, the controlling torque is provided by the spring. So at steady state condition, or at steady state condition, the controlling torque is proportional to the deflecting torque, and TC is equals to K theta, and theta is the deformation in the spring. That is equals to it is B I L is also N and D. Okay. Now, if you see theta, there is a reflection is equals to N L D B upon K. Okay, and this is your I. So if you take, these are the constant, because this is the constant of your instrument when it is designing. So these are the designing constant. Let it's G. It is G. So your theta, the deflection is directly proportional to the quantity under measurement. इसका मीनिंग क्या है वही देखते हैं. Suppose 1 degree is corresponding to 1 milliampere, then 2 degree is corresponding to 3 milliampere, and 10 degree is corresponding to 10 milliampere. Clear है यहाँ से बात? So your deflection is directly proportional to the current. That means if you move 1 degree, then it is 1 milliampere. If you move 10 degree, then it is 10 milliampere. This implies that your instrument is linear. So the next point of this instrument is scale of the PMMC instrument is linear. Okay. So your PMC instrument is having linear scale. Okay. Now, if you draw the curve between the output upon input, this is, if you follow the Ohm's law, if any relation is following the Ohm's law or the y equals to mx line, then that is linear, na? So let's check. This is your theta output, and this is your input, that is current, and this is G. So this is the graph of your instrument. Okay. And if you have the sensitivity is what? Sensitivity of your instrument is, it is output upon input. So output is what? Theta, and it is current is input, then your sensitivity is G, and G is what? If you see the G is this N L D B and the constant of spring. So your sensitivity of the PMMC ammeter is depending on the number of turns, length, dia, magnetic field, and the spring constant. Hopefully यहाँ तक सारी बातें समझ में आ गई होंगी अब आपको. So we have just take working, then the deflecting torque, and how your instrument is linear, then sensitivity and its graph and its linearity. So अगले पार्ट में अगर हम देखें तो अब हम बताएंगे इसके I think one more torque is remaining, that is your damping torque. So now let's start your damping torque. So we have covered the deflecting torque and the controlling torque. the last torque in case of a diffracting instrument is what? Damping torque. So अब हम देखते हैं PMC instrument में damping torque कैसा होगा. Let's start. So up to here we have seen the deflecting as well as the controlling torque for the PMMC instrument. Now if we see the damping torque for the PMMC instrument, now in case of your PMMC instrument, damping is provided by the eddy current. Now the reason to use the damping current is first, the instrument which will have the highest operating magnetic field is better to use eddy current damping. Okay, because ऐसे इंस्ट्रूमेंट जिनमें आपकी जो ऑपरेटिंग मैग्नेटिक फील्ड है अगर वो वीक है और आप वहां एडी करंट डैम्पिंग यूज करेंगे, देन योर डिफ्लेक्टिंग टॉर्क इज नॉट रिक्वायर्ड एज वी. सो दैट्स व्हाई इन केस ऑफ पीएमसी इंस्ट्रूमेंट we are using your eddy current damping because the operating magnetic field of the PMMC instrument is highest. Okay. Now your damping torque or the damping is proportional to your damping torque is proportional to, let's say your damping torque is proportional to the speed. Your damping torque is proportional to speed. It is a derivation, but derivation is not required in case of your syllabus because we take just conclusion. Now first thing, eddy current damping and air friction damping and the last damping is what? Fluid damping. Okay, so we have three type of damping. Okay, so eddy current damping is used in those instruments whose operating field is highest. So the first example of eddy current damping is used in PMMC instrument. So the first example is PMMC instrument. Then the next example is hot wire, and then next is your induction type instrument. So we have three type of instrument in which we are having eddy current damping. Now the air friction damping is used in moving iron instrument, and electrodynamometer type instrument. And your fluid friction damping is used in electrostatic type instrument. ठीक है यहाँ तक. So we have three type of damping, that is the eddy current and air friction, fluid friction damping. Okay. Now if you see from the damping torque equation, if speed is zero, then your deflecting torque is zero. That means your deflecting torque is existing when there is a movement or there is a motion. If there is no motion, then only we are having two torque, the deflecting torque and the controlling torque. Okay. Now how the damping current is provided in case of your PMMC instrument, let's see. Now as a moving coil, as your moving coil is moving in the magnetic field provided by the permanent magnet. Okay, as the moving coil is moving in the magnetic field provided by the permanent magnet, then according to the Faraday law, the flux of the permanent magnet is cut by your cylindrical core, and your core must have only the one property, that is the magnetic property, that is low reluctance and high permeability. But your core is showing the undesirable property, that is the electrical property, the electrical conductivity. So due to that conductivity, it is having some resistance. That is the magnetic resistance. Okay, let's start again. When moving coil is moving in the field provided by your permanent magnet, this magnetic field is cut by the moving coil core. Now core is having undesirable property, the electrical property. Then according to the Faraday law, an EMF is induced in your cylindrical core. EMF is induced in a cylindrical core. Now your core is closed. Then there will be circulating current. That these circulating current are known